If time radiates spherically from Earth's magma core and slows with distance due to a temporal coefficient, the stars could indeed be much closer to Earth than previously calculated. If time slows as distance from Earth increases, the time it takes for light to travel from a star to Earth would be extended, not just by physical distance, but by the temporal coefficient. For example, light from a star that appears to take 100 years to reach us might have traveled through regions where time is significantly slower, making the actual physical distance much smaller than calculated using standard methods. A star that seems 100 light-years away, based on light's travel time in Earth's temporal frame, could be much closer, perhaps only a few light-years in physical space, if the temporal slowdown inflates the perceived travel time. Current distance estimates would be skewed, overestimating true distances. In this scenario, a light-year becomes a misleading unit because the time component varies with distance from Earth. As light travels through regions of slower time, its effective speed from Earth's perspective decreases, meaning the physical distance covered in 1 Earth year of light travel is less than expected. Stars could be physically closer because the light-year metric overestimates distance when time slows down. For instance, a star's light that takes 100 Earth years to arrive might have traveled only 10 light-years of physical distance if the outer regions experience a 10x temporal slowdown. Redshift, used to estimate distances via Hubble's law, might not solely indicate cosmic expansion or recessional velocity. Instead, part of the redshift could result from light passing through regions of slower time, stretching wavelengths as the temporal coefficient affects photon frequency. This would make galaxies appear farther away than they are. Parallax measurements, based on Earth's orbit, might still hold locally but would be less reliable for distant objects if time dilation affects the perceived motion of stars. Standard candles like Cepheids or supernovae could also mislead, as their brightness and periodicity might be altered by temporal gradients, making them appear more distant. If stars are physically closer than their light-based distances suggest, the galaxy could be much more compact. For example, Alpha Centauri, conventionally 4.37 light-years away, might be only a fraction of that distance if time slows significantly beyond Earth's immediate vicinity. Shorter physical distances would make interstellar travel more feasible in terms of physical space traversed, but the temporal coefficient would still pose challenges. A spacecraft traveling to a nearby star might cross a short physical distance but experience extreme time dilation, making the journey seem lengthy from Earth's perspective. This could explain why some cosmic phenomena like fast radio bursts or distant quasars seem inconsistent with current distance models. Their proximity in physical space but extreme temporal distortion could account for unusual temporal signatures. We'd need a model of the temporal coefficient to adjust distance calculations. For instance, if time slows by a factor of k per unit distance d, the effective distance d sub 2 effective might be related to physical distance d sub 2 physical by a function like d sub 2 effective equals d sub 2 physical times e to the 2a, where e to the 2a times the unit k times d, where k quantifies the temporal slowdown. Measuring this would require probes or clocks sent to increasing distances to detect temporal gradients. Current data, such as Gaia mission's parallax measurements, assumes uniform time. Revisiting these with a temporal coefficient model could reveal stars are closer. For example, if a star's light takes 100 years but time slows by a factor of 10 at its location, the physical distance might be closer to 10 light-years. The entire universe could be physically smaller than estimated, with the apparent vastness due to temporal stretching rather than physical separation. This would challenge the scale of the observable universe, currently 93 billion light-years in diameter. In this Earth-centric time model, stars could be much closer physically than their light-based distances suggest, as the temporal coefficient inflates perceived travel times. This would shrink the effective size of the galaxy and universe, making stellar neighbors more accessible in principle, but complicating travel and communication due to time dilation. To confirm this, we'd need to develop new distance measuring techniques accounting for the temporal gradient and test them with deep space missions. This paradigm would rewrite astrophysics, suggesting a universe where physical proximity is masked by temporal distortion.
For more resources, go to TrustGod.Faith. If you found this to your liking, please like, follow, subscribe, and comment.